Hi there, this is Krishna from San Jose, California, and my research is about optimizing SNN learning. Clustering is the process of grouping similar data, and it's incredibly useful, from biomedical tools to Google's web indexing. Modern neural networks excel at this, but are incredibly energy intensive. They require hundreds of watts, making them impractical for power-limited environments. Spiking neural networks, or SNNs, were first developed in the 1990s and show promise in this use case because they require just milliwatts by mimicking biological neurons. However, the most common learning rule for SNNs, spike timing dependent plasticity, or STDP, struggles to scale for larger practical tasks. And literature shows that SNNs, when trained with this learning rule, can have their accuracy lag behind normal neural networks by up to 40%. My project addresses these challenges with a two-step approach. Firstly, mathematically deconstructing SNN learning behavior, which remains largely unexplored, before developing an improved learning algorithm for larger tasks. To deconstruct SNN learning, I use dynamical systems theory to extend the basic one-to-one connection to the multilayer case. But due to the recursive nature of spiking neurons, where weight influences spiking rates, which then determines weight updates, I applied a quadratic approximation to model spiking. Expanding this to the multilayer case, I found that STDP networks are fully dissipative systems with unstable fixed points, and that the learning rate actually acts as a bifurcation parameter, which means that it determines whether the network is stable or chaotic. And you can see this empirically as well. So over here, I've trained a basic two-layer STDP system on the MNIST dataset. And when I run the script here to collect the Lyapunov exponents, essentially measuring the magnitude of chaos, you can see that there's this region of parameter options here where stability and chaos coexist at a spot where I like to call the edge of chaos. So after months of trial and error, my solution came through two breakthroughs: variable plasticity and triangulated attribution. With variable plasticity, I set the synapse's learning rates to naturally decrease over time, while frequent weight updates keeps it sensitive. This allowed the network to self-regulate between chaos and stability, and switch between excitatory and inhibitory modes. However, this has an issue, because chaotic networks can now spiral out of control while stable networks freeze. To counter this, my second algorithm, triangulated attribution, lets multiple synapses detect shared spiking mismatches and attribute it to a synapse upstream, preventing instability. Mathematically, clustering algorithms lack information for training weights, unlike supervised networks. The key aspect of my method is that they guide weights by creating and destroying saddle points in the optimal region. They do this by setting a dynamic eigenvalue distribution that can be controlled by just a few constants in my algorithms. For the sake of visualization, you can imagine here that the ball represents the weights. In MesoNet, the bipolar magnets, representing attractors and saddles in the network space, guide the weights in the optimal direction. Experimenting with these algorithms was my favorite part. I came up with ideas by looking for real-world analogies. Like for variable plasticity, I thought about how unchallenged beliefs grew more rigid over time. Then I connected these to mathematical concepts, refining ideas through trial and error in order to justify each theorem. I then implemented and tested variable plasticity and triangulated attribution, my two algorithms, on a split and merge architecture. I benchmarked various other models across 5 datasets and found that MesoNet outperformed previous SNNs in speed, accuracy, and efficiency. It performed best on CIFAR 10, demonstrating an 18% improvement in accuracy over the previous state of the art. It also demonstrated fascinating self-organization with a Turing map of excitatory and inhibitory neurons, revealing the emergence of actually cortical-like folds. MesoNet lies within 5% of the top traditional neural networks' accuracy for just half the energy consumption, which could have significant impacts across various applications like medical implants, deep space missions, and remote sensing. I became interested in this problem because I'm really passionate about neuroscience and its possible applications in technology. Thanks for listening, and I look forward to the fair.